In this video, I would like to give you a short update on our improvements in the measurement process for variational quantum eigensolver if you would like to solve the electronic structure problem. And then there are three works here that will be mentioned. Two of them are quite recent, and one actually inspired some of the ideas that came out in this two. And now the whole problem really could be related to the fact that even in 2022, on the modern quantum computers, what we can measure is not different than what Stern and Gerlach measured 100 years ago, which is the projection of the Pauli operators, right? And the whole problem of the measurement is that we need to have an expectation value of the more complex operator, which is Hamiltonian in this case. Now, when we talk about the electronic structure Hamiltonian, we usually start with the second quantized form right here, and using Jordan and Wigner transformation, we can kind of make a operator which is in a qubit space, right? Is a spectral, and that the qubit operator is just a linear combination of Pauli products P's here. Okay, now we cannot measure the entire Hamiltonian in the qubit space because it contains not only z operators but x's and y's. And so what we usually do, we partition Hamiltonian into fragments, a chance that we can rotate into fragments that contain only z operators. You can think of them as Hamiltonian fragments. And this partitioning is needed because we cannot simply rotate the entire Hamiltonian at once. That would be equivalent to diagonalization, which we're trying to solve with the VQE process anyway. All right, so then this partitioning requires us to approach the measurement of the expectation value of the Hamiltonian through measurement of parts, right? And for each part, we prepare a wave function and do extra rotation, measure Zn. And that measurement gives us essentially expectation value of the fragment. We will need to repeat it many times because the wave function that we prepare is not necessarily eigenfunction of operator we are measuring here, and it will be distribution. Now the requirements to this process are quite simple. Unitary that we have here needs to be quite simple, both on classical and quantum computers. On a quantum computer, it needs to be simple because we need to implement it in circuit, right? On a classical computer, it needs to be simple so that we know what we're going to measure, this big Z and operator. And the second condition, as I said, the wave function is not an eigenfunction generally of the fragment. So we would like to have fragments where the number of measurements we need to do is low, and that's related to variance of this operator on the wave function. All right, so you can do decomposition using algebra of qubit operators. Here's one example where we partition Hamiltonian into parts, where parts are linear combination of Paulis that commute. And then it turns out that you can use Clifford transformations for linear combination of commuting Paulis to turn them into these Z fragments, or Eisen fragments that we can measure. Okay, so finding these decompositions are quite simple, actually. If you think of a particular operator, which is a linear combination of Pauli products, I skip the coefficients here, and then it turns out you can map the Hamiltonian into a graph where each term is really a vertex, and you connect vertices by sort of edges when they commute, and don't connect them when they don't, right? And then finding the sort of fully commuting fragments, it's equivalent to finding the fully connected subgraphs, which are called cliques. So there are various heuristic algorithms to do that, because really minimum clique cover problem, finding the minimum number of such fully commuting sets is NP hard, so we don't want to do that. Also, it turns out that it's not necessary to find the minimal number of fully connected subgraphs, because that's not the most optimal way to go, since we are not really into minimizing the number of fragments that we measure. We are into a problem of minimizing the number of times we measure them. So those are two different problems. And it turns out that if you use simple greedy heuristic, meaning that you first try to find the kind of the biggest fragment with all Pauli products in it commuting, and then from whatever is left you find another big fragment and so on. So that strategy works the best in this case, and we will understand why in a moment. Okay, so then you can also do the decomposition in fermionic space. How do you do this? You can break down the Hamiltonian into fragments that can be solved using the orbital rotation or Hartree-Fock solvable. And if someone asks you what is the most general form of the Hamiltonian that can be solved using the Hartree-Fock method, another way to say what is the most general fragment whose eigenstates are Slater determinants, we all know that, say, one electron Hermitian Hamiltonians like this can be turned into a linear combination of occupation numbers using orbital rotations, right? So orbital rotations here. And why is this helpful? Because for the measurement, because occupations will be turned to Z operators when we do Jordan-Wigner. We also will have some qubit representation for orbital rotations. But the problem with this idea that we have a Hamiltonian that is not necessarily one electron, it's actually two electrons. So in order to generalize this simple thought, we can just simply go and make the sort of the middle part here, not a linear combination of occupation numbers, but really a quadratic form where we have a matrix lambda PQ multiplied by corresponding occupations, and orbital rotations are still sandwiched in that part. And if you just do orbital rotation on that part, it will become just general two electron operator that you may not even recognize that it's actually solvable by Hartree-Fock method. So such fragments we can use to formulate measurable fragments in fermionic space, because they will be eventually mapped to the qubit space where we can rotate them to the fragments with only Z operators. How do we find such decompositions? It's a nonlinear optimization where we sort of minimize this difference, the norm of this difference really, of the total Hamiltonian minus a sum of such parts, right? And in each part we optimize the unitaries and lambda matrices for each fragment to minimize this norm. So this is a non-linear optimization, but it is polynomial in cost because the number of parameters is polynomial, but we are not sort of insured from not getting to the local minima. So that's a possibility, but it works pretty well. Now there is a simpler version of this, which was actually reported in this work. And that simpler version is really using, instead of the full rank lambda matrix that we use, rank deficient form that where lambda matrix is really an outer product of a single vector epsilon, right? And if you do the decomposition in these forms using these fragments, they are equivalent to just squares of the one electron operators. The advantage of this simpler form is that you can obtain it, it's described in this work, using diagonalization of the two electron integral tensor, or SVD procedure of two electron integral tensor. So it's a much simpler procedure than nonlinear optimization. All right, so now, but we are not, as I was saying before, into reducing the number of fragments. We would like to reduce the number of measurements, of course. And simple theory here is that if we partition the Hamiltonian into fragments, right, and measure them the fragments, dealing with the wave function that is not an eigenfunction of the fragment, and we would like to minimize the number of measurements, large M. Now, what's the theory here is, like, let me illustrate in a simple example. If, say, we have a Hamiltonian that consists of two fragments, in order to get the expectation value of the total Hamiltonian with the accuracy epsilon, you will need this many measurements, M1 for the first fragment and M2 for the second fragment, and epsilon will be related to the variances of the Hamiltonians fragments and the number of times you measure them, right? So if you want lower epsilon, you need to have a large number of measurements for fragments with large variances. Of course, one can ask the question how to optimally partition, say, a certain measurement budget in order to get a certain accuracy in expectation value. That can be done using Lagrange multiplier methods. And as you could expect, the number of measurements for fragment with respect to the total number optimally is related to the ratio of variance for that fragment. So the larger variance of the fragment, the more time you need to measure it in the total measurement budget. And the optimal number of measurements, if you do the optimal splitting between the fragments, is given by this formula. So here we have 1 over epsilon square scaling. So the higher the accuracy, of course, the more measurements you need to do. And then the dependence on the variances of individual fragments in this optimal splitting is dictated by this sum over square roots squared. Now, this is an interesting form, and we can actually look further. What do we learn from investigating the algebra of this expression? So what does it teach us? The first message really that one can extract is that uneven distribution of variances are better. Why is that? We can simply slightly massage that expression by taking out the sum over variances. And what is going to be left here, we can define this ratios of weights of individual fragments, right? And these weights will be variances for fragment divided by sum of variances. And the interesting thing about this prefactor is that it actually, for two fragments, look like this with respect to the weight. So with two fragments, weight of one is omega, and weight of another, say, 1 minus omega, because we sort of normalize the sum to 1, right? And then there is this arch that shows that you would like to be somewhere closer to a large weight for one fragment and small weight for another fragment, right? Not in the middle. And interestingly, this can be connected to informational entropy that is given by this for the distribution with weights omegas, right? And even though this expression in the square brackets is different than, well, than entropy, but you can easily show by doing optimization or asking the question which distribution of weight will maximize the expression in the square bracket and entropy, and it turns out that the maximum will be for the uniform distribution. So the maximum will be somewhere here in the middle. You would like to stay away from the middle. You would like to have some fragments large and some fragments small. And that is perfectly achievable by using a greedy algorithm. Why does it happen in greedy algorithm? Well, one can think of greedy algorithm, let's say, if we have some nonlinear process like filling the square with the circles. The greedy approach to this problem would be making the first attempt a biggest circle and then filling the rest with the smaller circles. So the same sort of idea is applicable here, that when we partition the Hamiltonian using greedy approaches, the first fragments are always the biggest and they naturally have a larger variance. Now, another message, which is more straightforward, actually, if you want to optimize the number of measurements, you can simply try to take the wave function, which is an approximate wave function, and efficiently can be calculated on a classical computer, like say Hartree-Fock function or configuration interaction single and double, right? Some surrogate wave function, and try to optimize the variances for the partition that you use, or try to optimize the fragments so that the variances are smaller. So with these two ideas, sort of, we can go on. And the first work that we actually done back in January 2022, it's the idea that when we do the partitioning, let's say we have a Hamiltonian like this, where we have, say, 3 terms with coefficients C1, C2, C3, and they commute in this way that Z1 commutes with Z1, Z2, and Z1, Z2 commutes with X1, X2, but the X1, X2 doesn't commute with Z1. So you can partition this Hamiltonian into fragments, and Z1, Z2, the middle guy, can go into 2 fragments at the same time, and that improves how many times we sort of get the information about Z1, Z2. Now, expectation value is linear with respect to coefficients, so we can actually take this Z1, Z2 with different coefficients in different fragments and optimize this kind of splitting between the fragments so that, say, variance of these fragments is different or lowers, right? Because variances are nonlinear with respect to the coefficients. And that's what we use here, that expectation values are linear with respect to coefficients and variances are not. Also, we can optimize the number of times we measure each fragment because we know what the optimal sort of distribution of measurements should be. And so the variables in this scheme that one can actually optimize the coefficient splitting and the number of times we measure fragments. Now, the 2 schemes that we suggested in this work, it's a measurement allocation, where we just simply put the Z1, Z2 in both fragments with the same coefficients, and then we just simply optimize the number of times we measure. Those are the only variables in this simple scheme. And more sophisticated scheme where we also optimize the coefficient is number 2 here. But this idea of changing the fragments to lower variance sort of introduced even further, more optimal ways of creating the fragments, right? So if you can change the fragments to improve the variances, what prevents us to introduce some, say, Pauli products that were not initially in the Hamiltonian? And again, because the expectation value is linear with respect to coefficients of those fragments, we can add and subtract extra terms with the idea in mind that these extra terms, they will commute with the fragments participants, right, that come in from the Hamiltonian. And then when we sum all the fragments, they will be gone like ghosts, essentially. We call this sort of ghost protocol, where we introduced ghost Pauli products. Okay, and the same idea of optimizing the coefficients of the Pauli products that are present in multiple fragments, and also optimizing the coefficient of the ghost fragments. So that's the 3rd scheme that was reported here, and we call it generally shareable Pauli products because these Pauli products are generally shareable, and they involve ghost Pauli products and the Pauli products that just simply present in multiple fragments of the Hamiltonian. All right, so this was the qubit techniques, and the next idea, can we do optimization in the fermionic space as well? And we start simple, just to see how the fermionic space would work if we try to optimize the variance of fragments, or rather, I'd say, when we not only care about how we partition Hamiltonian, right, but we also care that the fragments that we have lower variance, right? So you can construct a functional like this, and we'll try to sort of minimize or optimize the parameters really of the fragments so that this value is actually minimal. Not only fragments sum to the Hamiltonian, but also they have low overall variance. Now, this optimization turns out to be hard. There are two reasons for that. First, we deal with nonlinear optimization because of these amplitudes of the orbital rotation in each fragment. And also, when we do these manipulations with the phases and with lambdas, we can simply going after reduction of the variance, we can break the sort of fact that the sum of the fragments give us Hamiltonian, right? So these two terms can compete with each other, and that makes the optimization difficult. Now, the idea that allowed us to improve overall fermionic scheme is that we would like to find, it was very productive to find something shareable between the fragments in the Pauli product case in the qubit space. And here we just need to find something similar so that we can move between the fragments and optimize how much of that shareable material can we move so that the overall summation of the fragments of the Hamiltonians to total Hamiltonian will not be jeopardized, but the variances of fragments could be improved, right? And so we found such fragments inside the fermionic fragments. Now, this turns out to be one electron terms, because one electron terms, they form Lie algebra. What this means is that if you have one electron Hamiltonian and you have another one electron for Hamiltonian, they are diagonal in using like a sort of you can obtain diagonal forms of those two fragments using different orbital rotations. If you sum them, you obtain still one electron fragment, which you can still diagonalize maybe using third orbital rotations, right? And no matter how many one electron orbital fragments you combine, you still can do this. So they are naturally can be moved between the fragments. All right. So now if we go to our general form of the fragment, right, it has diagonal and non-diagonal parts in this expression here in the brackets, right? And we put aside the non-diagonal part for a moment, but with diagonal part where P and Q are the same, we have this idempotent relation for the occupation numbers. They are projectors, really. That's why this is true. And what this allows us to do is that we can introduce the fraction of the diagonal fragment for each fragment, really, that stays in the fragment. And then there is another, like 1 minus that fractional value that we can take outside of the fragment and put it in a sort of collecting one electron part. And naturally, then we can optimize the variance of fragments by optimizing these fractions that we take out of each fragment. And this is just linear optimization. No matter how much we take from each fragment, we do not kind of change the fact that the fragments sum to Hamiltonian if they did initially. And so that is very kind of good process to perform, because it is simple and it allows us to lower the variances of the fragments. We call it fluid fermionic fragments because now our fragments become somewhat fluid in terms of how much of these diagonal parts can we have for the optimal variances. And let me just share the overall assessment plot, where we have measurements in millions to achieve milli-Hartree accuracy and expectation value for this small set of molecules. In the papers, actually, we had a bigger set. And it's a small basis, but still problem is challenging. As you can see, we're talking about millions of measurements, right? And for each molecule, we have 4 techniques. Red and gray are fermionic and qubit techniques, where we do not optimize the variances. We just use greedy approaches, okay? And then orange and blue. Orange is a fermionic with the optimization of the variance, which is a fluid fermionic technique. And blue is a qubit variance optimization techniques, which are shareable Pauli products, everything essentially, and the ghost and finding the coefficient splitting. So everything goes there. And the message here, I guess, if you look at all this, is that fermionic methods are generally better. After all optimizations, you can actually see that, I guess, orange bars, maybe only in beryllium H2, for some reason, which we don't know, fermionics are somewhat worse, but in all other cases, they are way better than qubit techniques. And we can compare these advanced techniques with the naive qubit-wise commuting grouping that was done in the 2017 Nature paper here. One of the first works on a real device. And if we sort of use that simple naive technique here for ammonia, the largest system we considered, that would be 500 million of measurements. And so, as you can see, we went quite far away from that by probably two orders of magnitude. Right, and now it's actually the best technique is less than 1 million of measurements. And to put this in some perspective, 1 million of measurements, if you push the time on the how quickly can you do operations, on the optimistic side, 1 million of measurements could be pushed probably to 1 minute. And then 500 million of measurements that you needed before for ammonia, it's 10 hours. And 1 million measurement or less for ammonia now, it's less than 1 minute, which is, as you can understand, big achievement. Now, to summarize, we found various ways to sort of minimize the number of measurements. And if you interested in sort of minimize the number of measurements, it's not only about finding good fragments, but also looking at the sort of error. And you can do it in fermionic and qubit algebra space, right? And different fragments involve different optimization methods, but there are some common features like greedy techniques help, and exploiting this non-linearity of the variance and linearity of expectation values also helps a lot. Now, overall, if you put everything together, number of measurements is better in fermionic methods so far. And more details you can see in these 3 works that are on arXiv and soon appear in journals.